And then we start the slide. And I think this is where we stopped the last week. We also have a few slides to finish. And so what we were talking there is talking about, let me just adjust this thing a bit. And we were talking about the discriminability, and essentially means how many different values you can easily see from the visualization. And the example we used there was a trade between the EU countries. So each circle is a country, and the line indicates how much trade is there between the two countries. The thicker the line, and the more trade. And so if you look at the legend here, and it indicates the amount of trade at 100, 250, or 500 millions. And you can see at this level, it's still possible to see the difference between the width of two lines, especially when they are next to each other. But if you want to add even more finer difference, for example, if you want to have a value called 150 between 250 and 100, you can see the difference between the lines becomes too small. And you can imagine if the two lines are not next to each other, it'll be quite hard to see. And so in that sense, in that case, would say the discriminability of line width as a channel to represent some attributes is limited, as it cannot show many values effectively, only can show a few. So this is one of the factors people will consider if you remember the list of the channels and which one is more effective. That's one of the channels, also one of the aspects that people will consider when they compare which channel is more effective. Okay, and then there's another factor which impact and how effective a channel is separability. So, and this is actually more talking about not individual channels, but interaction between two channels. And so, as we kind of mentioned last week, and if you have multiple channels, which we usually do, for example, color, size, position, and some of these channels are not completely independent from each other, in the sense, if you change the value of in one channel might impact people's ability to see the values in another. And so obviously, we prefer the channels are completely independent. So that means you can use them without affecting any other channels. That's what be a good thing. And if it's dependent, then usually that's a bad thing or negative thing, because once you change the values in one channel, it may have undesired impact on other channels. Okay, and so in terms of different type of research and the relationship between two channels, it can be completely separable, means they are completely independent, not affect each other, or they are integral in the sense they are integrated together. So it's not possible to separate them as separate channels. So in the case of the integral, if the two channels cannot be separated, they cannot be used to represent two different attributes. And because the change in one attribute would affect people's perception on the other attributes, even when there's no change. And then what we're saying here is, these are the two extremes. So one is completely separable and one is completely integrated. Obviously, there's a spectrum, so there's some other channels with somewhere in between. So as we already said, and if it's separated, then its visual encoding is straightforward because you don't have to worry about its impact on other channels. And then if you, as I always said as well, if the two channels are completely integrated, and if we want to use them to encode different information, and they will fail because people will not be able to see them separately. So I'm going to show you some examples now and to see if you can see different channels. Okay, and so this, let's assume this is one of the data validations. We're using various channels to represent some attributes from the data. And can you see which channels are being used here to represent these data, the data attributes? Or let's say how many can you see? Let me do a doodle. Let me do a poll. Where is the poll? Find it. Just creating the question quickly. Oh, not this poll. Let me choose. I can have multiple. And can you see the question now? And so the question asks how many channels are used to represent data attributes. And so the channels can be, for example, position, color, size, lens, etc., etc. Yeah, I had a few people voted. Can we have a few more? Okay. I'll give you maybe 10 more seconds and I'll stop the poll. Okay, okay. Yeah, I think most of the people already voted now. Okay, I'll stop there. So you should be able to see the results now. So I think about 60% of people selected 2, but there's also some people selected 1 and some people selected 3. Okay, and so maybe the question, maybe for the people selected 1, what is the channel that being used and to represent data attributes here? Anyone, you can either unmute or just maybe type in the chat. No one? Okay, and then let's go to group 2. So for the people selected 2, and they said you have 2 channels being used and to represent data attributes. And what are they?
Point and color.
And sorry, and I heard the color. What is the first one? Point.
Point.
Okay. Point and color. Anyone else?
Size of the circle.
Size of the circle. Okay, that could be potentially another one. So then in this case, we have potentially 3 attributes. And anyone? Okay, and Olusegun said, and in the chat says color and position. Okay. So I think most people would agree, and color is one of the channels because you can see, and some of the dots are blue, some are red. So obviously that probably means something, even we don't know exactly what it means. So that channel is to represent it. And also someone mentioned the size, and so far, and there is no change in the size of these different points. They all look the same size to me. And so there is a chance that it's not used to represent any data attributes. And because if it does, most likely you'd see different sizes among these circles. And also people, I think, mentioned point. And in this case, and point itself is not a channel, and it's more like a marker. And each point represents one items or one data items, or one data points from the data. And it does not, the point itself does not represent any particular attributes of the data point or data item. And it's the color, size, or position of the point to represent. So that's make it a marker. Okay. And also someone said the position. Also, I think that possibly makes sense as well. And you can kind of see the position of these nodes are different, points are different. And some are here and some are here. Okay. And so I would say quite the obvious ones are the color and position, because there are changes, varies among the data points. And also I can kind of see, oops, sorry, had this problem again. And there are two different groupings, and one is a grouping by the position, and the other one is a grouping by color. So you can say all the red ones are in one group, and all the blue ones are in one group. And so in terms of separability, we can say the color and the position are separable, completely separable, and it does not really affect your way. Say the change in one attribute or one channel would affect your perception on the other ones. Okay, and let's see another example. Again, sorry about this. Don't know why it's happened. Okay, and in this case, it's fully separable. So now we have a look of the second picture. And still the same question. And so how many channels do you think is used in this visualization? And you should be able to see a poll now. So is the visualization using 1, 2, or 3 channels? Okay, I can see people start voting now. Okay, I'll give you 10 more seconds to decide which one, how many channels being used. Okay, I'll stop the poll now. And so you should be able to see the result now. And only one people say it's only one channel. And there are 40% people say there's 2 channels, and about 60% says it's 3 channels. So maybe start with people with 2 channels. What are they? What are the 2 channels used here? Anyone? Or maybe typing in the chat. Okay. Sainu says size and color. Yeah. I think definitely, and the size of the circles change. That definitely makes sense. And also the colors of the circles change. Okay, that probably means it's also representing some attributes, categorical attributes, for example. That's 2. And also Sasek says position, color, and size. So Sasek probably from the 3 voted for 3 channels. And obviously the positions of these nodes change as well. So that's a certain attributes. So I would say yes, and there's 3 channels being used here. And so there's color, there's position, and there's also the size of circle. And so from the first one, I already know, say, there's no interaction or interference between the position and color. And so now we have the size here. And so I would say, happened again. So if you look at the groupings, and you can still potentially see 2 groups. And one of them is a grouping by the size. So you have these maybe big circles and small circles. And the other grouping is by color. So you have the purple ones and the blue ones. And so in this case, and there is a potential for some interference between these size and color channel. And because when the size gets really small, it might become harder to see the color. So in the sense of potential, but I think so far it's mostly okay and not too much difference. So it's not fully separable. There is some interference, but very limited. And similarly, you can do position and color. Oh, sorry, position and color, which already covered here. That works. And the position and the size, which is probably separable, and the position should not affect people's perception on the size. Okay, so I'm doing another one. Still the same questions. And how many channels do you think are being used here to show the data attributes? Okay, just 10 seconds and I'll close the poll. Okay. Okay, and you should be able to see the results now. And again, so there's very few people select one channel. So obviously there's more than one channel being used to present attributes. Again, there's a kind of not that big difference in terms of people selecting 2 channels or 3 channels. Again, and can you tell me what are the channels used here for people either select the 2 or 3, or even people you select the 1? Can you tell me what are the channels being used to represent? Okay, there's people, I think someone typed and shape and position. So I assume this is for 2 channels. So you can have these different shapes. Some looks like a circle, some looks like ellipse, and some look like these are still circles. And obviously there's size, there's bigger circle and smaller circle. Okay. And some people say shape. And okay, position, size, and shape. Okay. And people say position, size, and shape. That means probably the main one for 3 channels. Okay. And okay, obviously, I think they are correct. And but say some of them actually might not be the oh, one black again. some of them might not be the actual intentions of the original display. So you might potentially see 3 different groups. So you have these big circles and these ellipses and these small circles as a result of these different channels. And what actually the designer or the people creating the visualization, it was using the width of the circle to represent one data attribute, and then the height of the circle to represent another attribute. But I think no people actually said the width and the height are 2 separate channels. Instead of what they perceive is either the change in the shape of the circle or the mark, should I say, or maybe the size of the mark. So in this case, there's quite a bit of interference between these 2 channels. So if you want to use width to represent one attribute and height to represent another, and the user probably not going to see the visualization that way. Instead of they might see different shapes, which usually it means they will think, okay, that this means different type of product or categorical values. So this is when you're starting to see interference and between the different channels. Okay, and just have one last one. And sorry about I don't know why it's just went black again. Okay, and this is one last one. I'm gonna relaunch the poll again, so you're not very familiar with the question now. So how many different channels do you think has been used here to represent the data? Oh, there's people saying 3 and 2. Oh, 1 as well. Okay. Okay, 5 more seconds and then we'll close. Okay. And I hope we can see the results again. So 40% people select there's only 1 channel. And then there's 50, just about 50 says there are 2 channels, and only 7% people says, only 7% people say there are 3 channels. Okay, so whichever choice you made, can you just type in what are the channels used here? Can you type that in the chat? If you think 1 and just type 1, and if you select the 2 and type what are the 2 of those channels. No one? And okay, so okay, someone say color and someone say position and color. Yeah. And also someone say hue, which is a more technical name for the color, and position. Yeah, these are all correct. So obviously we can see different colors here. There's some gray, some purple, and some, oh, sorry, maybe this is more like a pink, and this is more like purple, and this is like a more teal or kind of green bluish color. Okay, and obviously the position of these nodes are different, so that's another potential channel. Okay, so what you potentially see here, you might see, and okay, maybe the color is one of the way you can separate these data into groups, data points, and just depends on the color of the point. So there's this kind of more reddish points was one color, one group, and the purple one a second group, and this green bluish color for a third group, and the gray one for. But actually, and what the people created the visualization, and he or she actually used the amount of red and amount of green to represent two data attributes. So it says if the, let's say, attribute A is represented with amount of red, attribute B is represented by the amount of green. So if the attribute A had higher values, then say there will be redder. And again, if attribute B has higher values, it will have more green than those. But what you see is the result actually making the mixing of these red and green colors. And it's almost impossible to see the individual changes of the red or the green. And so in this case, we will say, and there's a major interference between these two channels, red and green, or one may even say they are integral or completely integrated in the sense it's not possible to separate. As most people will not see it's a separated. You can't really compare, say, really these two, say how much red, the difference in the red between these two type of colors. And people would not see that way as well. Okay, and so that explains the separatability or the lack of separatability. And so one of the main reasons certain channels are independent and certain channels are integrated is just purely because how humans see these things. And another thing that's relevant to this, we need to kind of be careful or take advantage of, and is the pop-out effect. Okay, and so I'm going to show you some pictures, and then your job is to find the red dot inside the entire data collections, and just notice, pay attention to how long does it take for you to find it. So I'm going to show you first, and this one. So the red dot is here. I will assume most people should be able to spot it straight away. Okay, and I do this one, then most people would be spot straight away. The red dot is here, and this one might take a slightly longer time, and there's actually a red dot which is here, and then this one. Can you see the red dot? Yeah.
Yes.
Yeah, I'll just say by now you should be able to see it's roughly here.
Yeah.
And then this one.
Yeah.
Yeah. It will be here. And finally, this one.
Yes.
Okay.
Yeah.
Red dot is actually here.
Yeah.
Okay. And so this might vary a little bit among each individuals, but generally this is very fast. And you can always see the red dot straight away out of all the other blue dots. And this becomes slightly harder in the sense here, the color is all the same. The difference is in different shapes. And this maybe takes slightly longer time to spot, and the one that's of a different shape. And in general, this will take even longer. And because here it's not only the color, but also the shape changes among the different points. Then to spot the other one, and takes slightly even longer time. So, and in the visualization, what we're trying to do is try to do this type of visualization if you want the user to spot the other one. So that's your task. For example, you want to find the outlier. This kind of is the best because it's always the fastest. And this is actually something to do with the parallel processing and in the vision channels. And someone's so the ideal case is if you can find the answers, doesn't really matter how many points are there, which is usually like this case. You can imagine, so now this part has many more points than the first example, but you can still see the red dots almost instantly, the same takes same amount of time as you would see in this one here. And you can imagine, even you have even more blue points, maybe 1,000 blue points, you can still spot the red one very quickly. So this is a type of and visualization of visual design we want to try to make use of. So that gives you a very nice property. So even for very large data sets, you can still find the answer very quickly. And then, for example, for this type of visualization, if you need to find the odd one, you can imagine as the number of data points increase in the visualization, say you can have more circles and squares, have a few hundred or a few thousand, it will take a longer and longer time to find the odd one. So that's in the sense, or to say, have less pop-out effect. And it's something, sometimes you have to do that, but if we can, we want to avoid using this type of visual design. I would say this is maybe somewhere in between these two. So, and in some worst cases, and to find this odd one or different one, you have to do a serial search. In the sense, you have to look, actually actively looking for every point in the visualization to find that one. That will become quite slow, and if you have a large data set. So we want to aim for this type of visual design. Okay, and so besides color, so here we change the color, we change the shape of the marker, or the color of the marker, to as a way to identify the different ones. There's other things we can do as well, and we can change the orientation. So this is quite easy. You can see, okay, most of them are horizontal, only this one is vertical. It works quite well. Or in a general way, I would say just tilt. So it does not have to be vertical or horizontal. It could be, say, some angles as well. The next one is size, or just you say quite easy to see. And the next one is different shape. Again, quite easy to see. And this one becomes slightly harder. What it's meant to say is this is using approximate. Say these are kind of grouped together compared to these ones. I would say it's already a little bit slower compared to these ones to detect the difference in this one. Okay, and can anybody see which is the odd one here in this one?
No.
Yeah. There is an odd one, which looks visually a little bit different from the others, but this is much harder to see. And so actually the odd one is this one.
The
Shadow of, the
Yeah.
shadow of one point is on the opposite side.
So the
This-
difference is in the shadow direction. So the other points, the shadow is kind of towards the bottom right of the point, and this one is the top left.
Yeah, the opposite. Yeah.
This is different, but again, it takes much longer time to detect this type of difference in channels. So that's a not very good channels in terms of representing, if you want people to see the difference in the values. And then finally, there's this one, and which is meant to show and using whether a pair of lines are parallel or not to show. I think this is kind of okay, maybe slightly better than this, but not much. In terms, you can see this one is parallel, all the other pairs are not. Okay, and so when we do the visual design, you probably want to use these ones, which are very easy to see. And these ones, and sometimes you might have to, because you don't have the choice to use these ones, but then just need to be aware of the potential impact on, say, how fast people can identify and find the answer. So that's actually contributing to the effectiveness of the channel. Okay, and finally, we can talk about in terms show the different, how effective the channel to show different groupings. This is usually for the categorical values, and which can only tell whether two items are of the same type or not. And usually that's used to show grouping. And so these are the ones usually quite effective in the sense, and you can put a shape or a color the background around the data points of the same group, or you connect the points belongs to the same type of group together, so they can see the groupings quite easily. And this is usually okay as well. And by putting the points which are in the same group and next to each other, and that's usually a quite good one. And when you can't use it, you can use color to show the different categories or type of data points. Or even if you can't use color, then you can start using motion or shape. So somehow shape is actually not a very effective one, but actually previously when we tried to see the pop-out effect here, and shape is actually quite obvious one. Okay, and so that finished the kind of leftover from last lecture. And in terms of reading, so this is chapter 5 and of the book, and it talks about the markers and channels. So this is probably one of the most important chapter of the entire module, I would say. So I would say you should spend a bit more time just to make sure you understand these. Okay, and now we're going to move on to the lecture that was originally planned for this week. Okay, and this week we're going to talk about rules of sum. And essentially, if you remember, we used this term called idiom before. So that's like the design guidelines that you should usually follow. And the different, say, which channel is effective for numbers and which channel is effective for categorical values. And that's like the idioms. And the rule sums is very similar to the idioms, but in the sense, and it's less, how do I say, and there's more chance that these rules might not follow. And so for previously, maybe say the position is most effective and channel to show numbers, that's almost always true, and very rarely that rules will not be correct, whereas rules of sums and still correct in the most cases, but more likely there can be exceptions. There's more an instance of exceptions. Okay, and this was prepared just to give a quick review of the covered in the last week. And so we talk about markers and channels, and the marker is to represent the data points. So one marker is one data point, or we usually can think of one marker as one row in your spreadsheet. So we have 0D mark, which is a point. It is 0D because it does not have any, say, width or height. And we have 1D mark, which are the lines. So it only has one dimension, which is the length of the line. And then you have 2D marks, and it can be areas of various shapes. And it's possible to have 3D marks, but as we said, 3D shape is actually not very easy to see in visualizations. So that's usually not recommended. Okay, this is the list of the channels that's commonly used for different type of attributes. And for the numerical or the ordered attributes, there's these options. And then for the categorical, which you cannot do any computation or do any ordering, or you can say whether it's two data points are same or different. And these ones. And these are ordered from the most effective ones, which are on the top, to the least effective one, which is at the bottom. And again, for example, there's nothing stop you to map a number to a shape. It's still possible, and it just says that's so rare, and the effectiveness is so poor that's not even listed here. In theory, you can map any attributes to any visual channels you want, but usually these are the more common ones. These are the relative orders between these. And when you design a visualization, you should always pick the start from the top ones. And sometimes That's one of the first things you have to think about when you design a validation is, and which attribute is most important. And then once that decided, then you can say, okay, whether this is a numerical or ordered attributes or quantitative attributes, or is it a categorical attributes, and you can use that to represent. That's usually would give you a good start point. And on the quantitative or the numerical side, and the bottom half is usually the ones and you should avoid. So we can see the 3D volume is at the very bottom. That's why it's usually not used in the validation. Okay, so this week we're going to talk about, as I said, about rules of thumb. These are, again, is advice or guidelines, and usually have more exceptions compared to idiom. Again, this will be based on the current state of knowledge as people still doing research in this field. And so in terms of these rules can be a little bit ad hoc. It's not as, say, a coherent theory as, say, the channels for different type of attributes yet. And finally, they're saying, okay, these are not always correct, and there can be exceptional cases, and they can actually change as well, depends on the more research people and people do. Okay, and so the first one is called no unjustified 3D. And so some people might think, okay, 2 dimensions are good and 3 dimensions must be better. And if we can actually draw 4D graphs or charts, that must be even better. But this is not necessarily the case. So this is some kind of 3D visualizations, and you have these networks and then the connections between the networks and in 3D. Okay. And however, so because in the 3D visualizations, you're going to be using the depth, which is distance from the user, to encode information. Otherwise, it will become just a 2D validation. As we said before, and the depth is actually a quite poor channel to represent quantitative numerical data. You can see, and depth is roughly here. So halfway, and probably in the bottom half as well. So adding that one actually does not usually give you too much. You're probably better off to use, if you want to represent using depth to represent, say, a quantitative attributes, and you might be better off use some other channels to do that. And also, we add human to see the depth is very different as how we see the X and Y and the first 2 dimensions. That's why it's not very effective. And 3D viz or 3D visualization is definitely useful if the data itself is 3D. So I'm showing, say, a picture of a 3D scan of people's brain, and because the data is 3D, then 3D visualizations has to be used here. And this is a different visualization I created for network, which is also 3D. Not necessarily says it's any better or good choice. Okay, and so the general rule is to say, if you want to use 3D, and you have to be careful, and just to make sure it is actually useful. And this is also one of the reasons, for example, Tableau does not even include 3D visualizations. So most of the visualization it recommends would be in 2D, is because there's no specific, it's very rare. 3D is the best option. And also this type of visualization is not something you would see or use in Tableau anyway. Okay, and in most cases, it's just safer or better just to use 2 spatial dimensions. And then for the other attributes, you can use size, color, and these different attributes to represent additional quantitative attributes. And the possible problems with the 3D is because it could potentially have occlusion, and you can have perspective distortion and other things. Oh, I missed the the picture there. I don't know. Oh, it is. Okay, and so this is just going back to the list we saw before, and you can see most of these and highly effective channels are all 2D, and position, actually position itself is just 1D. You can have position for each dimension, 1 or 2, usually not 3, and then say you can see the length, which is 1D, and the tilt is 1D, and the side is 2D, and the 3D is only appear here. It's not a very effective channel. And similarly, if you remember this line, you can see the depth is here. So as the nodes becomes further away from the user, and the perceived changes is actually smaller, usually smaller than the real change in data. And so this is the potential occlusion, and which only happens or more likely to happen in 3D. And so occlusion just basically means the items in the front blocking the items in the back. So you can't see the one in the back. And usually this is a bad thing. So in this case, we're showing a network, and you have these nodes which are either red or yellow, and they're connected. And then the size of the node also represents some information. And because this is a large network, you can see the big nodes in the front, but for everything else in the back, either smaller or are being blocked. It becomes much harder to see. Really, and this is not a very effective visualization, except to say you can see, say, okay, there's quite a lot of nodes in there. They are all very connected. But actually, occlusion is very important in 3D, in the sense that's the most powerful cue for people to see depth. And so if you just see two nodes independently, for example, say, and this yellow one here, and this yellow one here, and it's quite difficult to tell which one is closer to you. Is that this one on the right, or is this one on the left? Okay, but if you have two nodes, let's say these two, the yellow one kind of blocking the red one, so you immediately know the yellow one is closer to you because it's blocking the red one. So actually, it's very important to have occlusion to see the items or perceive the depth. But the occlusion itself will stop you from seeing some information, which is not very good. Okay, and the things that make it, and because it's 3D, what you can do is that you can interact with the 3D, and then the occlusion relationship will change. So something that's not, say, not blocking before, then now will become blocking, and that will help you to understand the depth relationship between these nodes. And this is called the motion parallax effect, which actually makes it easier for you to see the 3D. And so actually, so it's important for you to, if you want to understand something which you have to display in 3D, then it's important to make it interactive so that people can, say, moving it. Let me see if this link still works. Oops, it's gone now. And so this is actually a 3D visualization. Unfortunately, the links no longer work, but it is actually something you can rotate and zoom in, zoom out. And once they start rotating, you actually can see, and it becomes easier to see what the visualization is like. Let me see if I can find something quickly. No, you can't really zoom these things. Okay. Yeah, and again, a little bit more in terms of the potential problem with 3D validations. They have this something called the perspective distortion. And it's quite natural, it happens to us all the time. And just we probably, because so used to it, we did not really even notice it. So all it says, it just says the object which are further away from you appears smaller, but also actually change their positions on the image plane. So this is what it looks like. So you can see in your mind, you probably think, okay, and these are all the line of objects. They are probably in your mind, you can say they are parallel and also about of the same size. But when you actually visualize them, you can see the same, let's say they are same size, the things that are closer to you, obviously bigger, and then the further away, they become smaller. But also, even these lines, your brain will tell you are probably parallel. But if you look at the images or the picture, you can see the distance between the lines actually are bigger as you're closer to you, and again smaller as it's further away. So that's what this means. And perspective distortion. Okay, and then what potentially it has say some visual, they will interfere with visual encodings which use positions and the size channels. So we already mentioned, we talked about just say at the beginning of this lecture or the first part, say the interference is say the change in one channel may affect the encoding in the other channels. So usually that's not a desired property to happen. Here, we're not talking about any channels. It's just because of this and 3D perspective we want to use, and that might make it harder to compare the size. For example, if you want to compare the size of these items compared to the one at the very end. First, the one at the very end is very small. It's already hard to see. And when you compare the two, it's almost impossible to tell whether this one looks smaller, is it because it's actually smaller, is it because it's actually further away, so it appears to be smaller, they're actually the same size. So that's interference introduced by just because you're using the 3D perspective, so make it harder to compare. And similarly, when you compare the position, when it's all aligned, it may be still okay. But let's say if it's not perfectly aligned, and there's another point, whether you want to say they are on the same line or not, might be difficult to see. Okay, and so that's another example. Say, for example, in Excel, I think you can create 3D bar chart as something like this. And the same information, and you can quite easily just create it using a 2D bar chart. So for example, each of these color is a separate bar chart. And the only downside would be, say, the 2D bar chart might need more space to display compared to the 3D one, but it avoids these problems. For example, it would not have occlusion. For example, these smaller ones behind, much harder to see. But also, for example, these smaller ones, it's very difficult to tell what their value is. And also, for example, compare these different ones at different rows, become very difficult. Okay, and the next one we're going to show you is kind of related to the dynamic or animations used in the validation. And so if you remember from the very first lecture, say we want to use visualizations, and because you want people to see the data, external cognition, rather than say remember and imagine what data is like in their mind. And because seeing data is much more effective and faster compared to try to imagine or remember what data is like. Okay, but then when you're seeing the data itself might change, and it's often easier to compare the changes in data, if you have two views, one is before and the other is after the change, and you have them side by side, and to compare the views, then is if the view itself is changing. So over the time, the view changes. Okay, and so I'm going to show you an example here. Hopefully this still works. Okay, I need to log in. Okay, and so what it's showing here is the, let me see if I had any higher resolution than this. No, and that's showing the flights and between the Europe and America. And so each dot, colored dot, not really colored dots, each bright dot is an airplane. And then the blue line is kind of the trace or the flight path of the airplane. And it shows, say, this is definitely before the pandemic, and it shows at different times where the flight taking off and the landing and how that changes over the course of a day. And so you can I see that? Yeah, the time is here. That's between 12 o'clock and 9 o'clock, and you can see all the flights how they're traveling at different places. And now it's between 9 o'clock and 12 o'clock. And there's even more flights now compared before. This is UK, so these are the cross-Atlantic flights happening all the time, and this is what's happening within the UK. And this is even later one. Okay, and so this is certainly a very interesting visualization, and you can spend. Okay, maybe we'll finish it. It's not that long anyway. It's Heathrow and Gatwick. Some of you will probably being there. It's probably most likely Heathrow. And you can also starting to see these kind of patterns where the airplane has to do certain maneuvers before it can land at Heathrow. Okay, and so this is coming to the evening now, which is between 6 p.m. and midnight. Okay, yeah, and that's it. And then kind of the cycle stops and starts again from the second morning. And so this is like one of the examples of showing this temporal data, or the data changes over time. So the data here is the flight and the flight of the positions and where they're moving over time, or the position of the flights changing over time. And yeah, and obviously the visualization is very nice, beautiful, actually impressive to look at. But the problem is, for example, if I'm asking you now, what the pattern is like in the morning between 10 and 12 o'clock? Can any one of you remember from the visualization? So I would say most of you can't remember, and I still can't. And even after watching the video many, many times. So this is exactly the point of the external cognition versus internal memory. And so while this kind of visualization is very kind of impressive, interesting to look at, what it doesn't show you does not show you the flight information at a particular time, or what the data is look like at different time points. You really have to remember yourself. And it's very difficult because there's so many things happening at any one particular time. And so if I want to ask you, say, does it have more flight in the morning or more flight in the afternoon? Again, you have to remember, and or even have, or potentially just go back more likely is go back to the video and say, go to the particular time point in the video and then going back and forth just to compare. Okay, and so the usefulness of this is good maybe for storytelling if you want to show something, either visualization to tell a story, and this will be very impressive or attracting people's attention. Okay, and it's good for showing the transition between the states. If you have only 2 states and you want to show the transition, that might be enough. But if you have many, many different states, it might be hard. So if you have many states, it becomes much harder. And so the alternative will be something like this. So this is not exactly the same data. The general idea would be, say, you have say, what are the flights look like at the midnight, 1 o'clock, 2 o'clock, 3 o'clock, so on and so forth. And so you will need a little bit more space because you have now showing multiple instances or multiple points, multiple states of the same network of visualization, and each particular instance would not have as many details as it would show in the animation, but at least you have a much better overview to see when it has more information. Say, for example, we can easily see maybe this part, the network is more dense, has more lines in it compared to the first and the last row, which is probably quieter. And this particular method is called small multiples. That's a particular term. So you have multiple copies of the same data with different, the data is changing all the time. So you have slightly difference between these different versions. Okay. And so these are the 2 kind of general approaches in terms of showing this. And you can have the animation, which we're showing here. And it's literally, in the sense, it's showing time with time. So as time goes by, it has how the time moves in the animation. And on the other side will be small multiples, which I look at these, and you're showing time with space. So say it is the position of these relations indicating what the time is. So you can see all different time points at the same time without having to remember them. Yeah, and so in terms of the rules of thumb or the general guidelines, usually small multiples and is recommended, even though it's not look as fancy or impressive as animation, but for most of the tasks, actually this will work better, small multiples. Okay, and the next one is about resolution and immersion. And so this is much more relevant now. And so you have these kind of headset, and which allows you to see things in virtual reality or sometimes augmented reality. And so essentially what you see is you see 2 slightly different images for your eye. So this will be the image of your left eye, and this will be the image for your right eye. So for me, I couldn't even tell the difference by just comparing these 2 views. And because the difference is really only maybe slightly moving all the image to the left a bit, and then maybe the distortion is slightly higher. That's all you see. Okay, but if you look, the left eye only see this left image and right eye only see the right image, and then your brain will merge these 2 together to give you a more 3D or realistic feeling. Okay, and then so there's certainly quite of interest in terms of showing data in virtual reality, presenting somewhere like this, something like this. Okay, and there's certain arguments against that idea. And so the first one is, say, immersion typically not helpful for abstract data. So maybe, for example, this one is looking at a room. So maybe 3D is quite useful, for example, if you want like internal design or architectural design. But imagine if you're looking at a bar chart. So first of all, it does not even have to be 3D, but if you have a 3D bar chart, looking at on let's say a flat screen, a monitor, and can imagine that compared to in this kind of way, it usually does not really help you too much if you look at the bar chart in a 3D way like this. Okay. So because the sense of the presence, which is one of the main advantage of virtual reality, does not help in, say, the simple charts like a bar chart. Okay. But also the downside of doing virtual reality display, or they call it stereoscopic display, which is the same thing, is you really only use half of the display, half of the space, and to display your information. Essentially, this information is duplicated twice. That means you're only using half of the space to show the information. That means the amount of space you can use for showing data is much less, in essentially only half of the space. And then we mentioned before, the amount of available display space, or the number of pixels, is a very important factor, and in terms and effective, or in terms of validation. And usually, especially when there's lots of data, if you have lots of data, you probably want more pixels or more space to display your data. So that will be a downside of using stereoscopic display or VR display. Then, yeah, essentially, as we said, you're really only using half of the display space to show your data. Okay. And then already said, sometimes it does not make too much sense to show the data because in 3D or virtual reality, because what you can gain is quite limited. So it's most useful and when it's important to have a sense of presence. So for example, if you want to explore a building, then maybe the sense of presence is very important in there. But if you want to look at abstract data, maybe as this one, it is probably less so important. So again, obviously VR is very interesting and attractive and fancy, but it is not always the best way or most effective way to visualize data. Again, we need to be very careful. So again, this goes back to the kind of the analysis framework you need to look at, and what the type of data is, whether it's, say, kind of and the interior of building or some abstract chart, and also what an analysis task is. So for the task, if the sense of presence is important, for example, for the abstract data, it's probably not. Whereas this type of data, maybe it is. And then you choose your validation accordingly. And okay, the next one is about kind of general principle, and when you try to show lots of data. And so more often than not, we will have more data than we can show on the screen. And also more likely you're going to have more data than we can see meaningfully at the same time. So not just display on the screen, but you can actually see them and discover something. And as we mentioned in the first lecture, what we can see at the same time is very limited. Say we did this example, we had this, and we have this work, and the first couple of labs will just look at the car data set, and it by no means a big data set, and it's just a normal it's a spreadsheet with a few hundred rows. But again, already, if we want to just show everything on the screen, it might potentially be already too much. And then later on, we look at this supermarket data set, and it's much bigger, but still it's not even the bigger size, say, among the data set we usually would have. And again, if you visualize everything in the spreadsheet at the same time, it will definitely be too many for us to see and detect any patterns. So here, so because these are very common problems, and so a general approach would be, say, overview first, zoom and filter, and details on demand. So I'm using, say, the old design of the Google Map as example. And so first you show an overview of the entire data set, and then give the user called a broad awareness of the entire information space. Okay, so what we're seeing here is we have this is an overview of a much larger, the entire North America. And this indicates this is a part which currently being displayed like this. So this is an overview, give user a broad sense of entire information space. And obviously this is something you need to design, because in this overview, you cannot show everything. You have to hide lots of information and only can keep the most important information. So in this case, in the Google Map, it only shows the name of the continent, North America. It does not show anything else, say not the cities, not the roads, etc., etc. Only showing the names and the shape of the continent. That's it. Okay. And then once you provide the overview, and the user more likely will need to see more than just the overview. For example, if the Google Map can only show you this level of details, it's not very useful. For example, if you need to navigate or say driving from point A to point B, this is not very useful at all, because it's not telling you and when to turn, which way to go, etc. Okay, so if you want to show something, and as we said, it's not possible to show all the details in the overview. So you have to do some zooming and filtering and aggregation. In a sense, if you want to show more details, you have to pick a much smaller or subset of the data set before you can do that. And which in this case is user might select this area, which is shown here. Now, because this is a smaller area, then more details can be shown. It can show different cities and the main roads between the cities, and maybe a little bit more details about, say, the states and the boundaries between the states, and so on and so forth. So this is where the zoom and filtering comes in, aggregation. So the user can control where to look at it and what level of details that they want to see. And then the details is only show an on demand. So even at the zoom and the filtering level, there are still lots of details cannot be shown. For example, and Google have lots of information about each city, which you cannot really show here. So what you would usually do is the user might click and on one of these cities or some other labels, and then the Google will pop up a window and show more details about that particular city. And that's what we call the details on demand. And then once people interested in a different city, usually if you click on a different city, let's say say Pittsburgh or New York, then the previous one will hide. So only the details for one city is shown at a time. So that's again quite common. Okay, and just to repeat, and so usually you try to provide an overview, and which is much simplified or aggregated. So you might be group items together, just show them at one point. And then when the user needs to see more details, usually the zooming in and filtering will be involved, and user might select a specific sub area of the data set, or user might even filter, for example, based on the attributes. They only see some certain part of the attributes. For example, in Google Map, you can choose, okay, I want to see, I don't know, the traffic information, or maybe the train lines, or maybe the roads, depends on different type of information you want to see. And finally, the details on demand. And so that's when you say, if you want the details about a specific data items, maybe you can use a click, which shows a pop-out window and shows actual details, or mouse over. And the exact interaction is flexible, but the general idea is, so the user needs to request, and then you show the detailed information. And you don't really show the detailed information of all the items all the time, which will turn out being too much. Okay, so this is not, again, so this is again kind of a high-level general idea. We kind of talked about this a few times already. And so what it says is function first, form next. And so function here just means how effective the visualization is in terms of answering or achieving the analysis, help user complete the analysis task they need to do. Whereas the forms means say how colorful, how beautiful, or how interesting the visualization is. So usually the function is more important than the form. As when we design, and especially for people less experienced, there's a tendency to give more weight to the actual form. Usually things, okay, and the more beautiful ones is definitely always better, or the fancy ones is usually the better ones. But that's, as we saw today, and it's not always the case. So we're already seeing this for, say, 3D visualizations, virtual reality displays, etc. And or even the animations of the temporal data. In terms of form, they're probably more interesting and more fancy, but not always more effective in terms of to supporting the tasks. Okay, and obviously the best visual design should be both beautiful and effective. So have both function and form. That's the best possible way, if we can achieve both. But usually you should start with function, which is to support particularly analysis and the data you want to. And then later on, once you design the visualizations, which you know is effective for the particular task you designed for, and then you can improve the aesthetics, so make it looks more interesting, or more beautiful, more colorful later as refinement. Okay, but the other way around, which is if you start with the aesthetics or start with the form, and it is usually impossible to add or make it functional later on, and it's usually very difficult. Or let's say whichever aspect you start with will take the priority over the other. And so if you start with functionality or focus on it, so that will have a large impact on the final design, and rather than say the aesthetics. So if you start with functionality, you can improve its aesthetics later, but what you can do might be limited. For example, if you pick the bar chart, you can try to make it look better later on, but how much more you can do to make a bar chart looks interesting or kind of attractive is limited. You can only do so much in terms of adding colors or maybe changing fonts and so on and so forth. And similarly, if you start with the aesthetics or how beautiful the thing looks like, and again, later on, you might be able to make it functional, but that might be quite limited in terms of what you can do. Okay, and then this, okay, we're going to show this kind of conceptual and diagram again. So this big circle and all these and crosses and squares and circles and indicates all different ways to design a validation. And what you want to do is to start with the entire space and gradually narrow down before you find the one which you think is most effective. And that should be measured by the effectiveness, not say how beautiful, which is potentially also useful. Rather than you start with a fairly small solution space and gradually move down, you potentially would miss the important solution. Sorry, the most effective solutions this way. Okay, and but in some cases, form is actually also quite important. Okay, and naturally, and people would prefer the things that looks more interesting or beautiful or colorful. And for certain user cases, for example, where the people's engagement potentially has a very important role, in the visual design, then you maybe have to give more weight to the form. For example, if you design something which is you want to present the result to someone else, for example, you design a narrative of something with data visualizations, then one of the very important part of the design is to make sure people actually would spend time to look at it. Otherwise, it doesn't matter how effective designs are, if people does not even going to spend time to look at it, then it will not achieve its goal. And then in that sense, the aesthetics criteria becomes more important, has more weight now. And so they have a different impact on your final design. Okay, yeah. So good visual form enhances effectiveness of the visual representation. Yeah. As I said before, is say the best design is have to be both beautiful and effective. And actually being beautiful, if it's well designed, can help the effectiveness of the visualization as well. It's not always say, if you want to make something looks more beautiful, we'll make the visualization less effective or functional. And it can be the other way around. Say, actually, by making it looks better, and also improve the effectiveness as well. That is the kind of ideal situation. But more likely, as we said, would recommend you to start with making it functional or effective before it making looks better. Okay, and that's the end of the lecture now. And so in terms of the reading, this will be the chapter 6 of the book. It is also just called Rules of Sums, and it has more discussions about the rules we covered today. Okay, and we only have a couple of minutes left now, so I think I will stop there. Is there any questions before I close the session?